Hello, my name is Keith Parsons, and you're listening to another episode of Heavy Wireless, a podcast that's part of the Packet Pushers podcast network. Today's episode, we'll be talking about AP client and power mismatch. Now, this has been a thing for, probably ever since Wi-Fi's been around. But a couple of weeks ago in Prague at WLPC, Connor Burke gave a presentation on this very subject, and he did such a good job, I thought it would make a great topic for this podcast. Connor, welcome.
Yeah, thanks for having me, Keith, and for the kind words.
Well, let's just jump right in with what is transmit power mismatch?
Yeah, so obviously when we're in our environments and designing our network, we have to abide by regulatory rules. And one of the big ones when you're considering your overall output from the antennas and the AP is your ERP limit. So within that, the ERP is a pretty simple calculation. It's all done in dBm, so it's really simple addition and subtraction. So your ERP is the sum of your transmit power minus the cabling loss between the AP and the antennas, and then the additional gain that you see from the antennas. Now, obviously, if you're using an internal AP that has the antennas inside, you can't actually affect that the cable loss or the antenna gain. You can only play with that transmit power that you have available to you. If you're using an AP that does have external connections, then the cable loss and the antenna gain are changeable. And one of the things that we'll notice as we kind of get into the more practical portion of our talk here is that whereas the transmit power that you're increasing or decreasing on the AP side is only affecting the transmit signal, the gain and the cable loss is bidirectional. It not only improves how well you're speaking to the client, it also improves how well you're hearing back from the client. So that's the general synopsis of what we're looking at when we're talking about client mismatch between, and then that'll depend kind of on the region as well. There's different regulatory numbers that you have to abide by, but we'll look at a simple EU standard that's also kind of practical in the US as well later.
So what makes clients basically weaker than APs?
Yeah, there's a few things that cause that innately. Technically speaking, a client can be transmitting or receiving at as high of an ERP as the AP is. For practical reasons, though, that's not going to usually be the case. Both because the antennas within typically an iPhone, a laptop, or a scanner are much smaller than the antennas that you would use on an AP. But not only that, most of these devices are mobile, so they're running off of a battery. And having a very high transmit power would dramatically drain that battery life and reduce the overall user experience if they're having to plug it in every 30 minutes to charge it. So because of that, they're usually transmitting at a much lower ERP than your standard AP would be at.
Now, I just want to inject a weird anecdote in the middle of this. We think of our mobile clients, phones, etc., as fairly weak devices. But I saw a test that someone did once in a stadium where they had a client device that was basically in hotspot mode, so it was connected to cellular, and then a second device was connected to the first phone, and they went to the opposite side of the stadium, and from phone to phone, even with the weaker antennas and the weaker transmit power, they could talk and send data through. So Fernay and I went out to a football field, a U.S. football field, but we went to the end zone. So we were a little over maybe 110 meters away from end zone to end zone. And we were pushing a good 10 meg of data rate from iPhone to iPhone. So just because the power's lower and the antennas aren't as good doesn't mean that you can still go quite a ways.
Yeah, and I wonder if there's something in there that when you put it into hotspot mode, if it allows it to kind of exceed what it usually does for the RP and broadcast at a higher power. I'd be interested to see that
Oh,
actually.
that'd make a fun
I hadn't
test.
heard that.
But
Yeah.
in general, though, APs transmit further than client devices. Is that
In general.
yeah? And so it's well at a certain level, because I've given this example for a long time when people say, well, 2.4 goes further than 5 gig. Well, if you had a 2.4 and a 5 gig AP, their signals would hit the moon at the exact same time.
Yeah.
They would hit Jupiter at the same time. So it's not like one goes faster than the other. It's the receive sensitivity allows that a 2.4 has a bigger antenna, so it has more receive gain, and so that's the differential. It's not like inherently 5 gig doesn't go as fast or as far. So they have different ranges. How does that affect performance?
Yeah, and so the different ranges runs into that range asymmetry that you'll sometimes hear about, to where you'll have your client device and it's hearing the AP at whatever 100 feet away in a warehouse excellently, but it's having a struggle talking back to it because it is speaking at such a lower transmit power. So that's where that general range asymmetry comes from. And you'll typically see that more when you're using just the internal omnis of an AP. Uh, and that's why in a lot of these predictive softwares, Ekahau, Mina, Ivy Wave, NetAli, Cytos, you'll have those offsets that you can go in and set so that you can see more truly the ranges that you're going to be playing with when you're using your client device, because that's going to more accurately show the range where it's actually being effective. Um, I still think a lot of times designing without an offset is preferable, but there's benefits both ways, and I think you just kind of need to flip flop back and forth throughout the entire design to really get the best solution. But it is there for a reason.
They're having taught wireless design for quite a few years. I don't like thinking about the offsets
Mhm.
or applying them with just here, let's hit a button and that's what we have. There's a lot more thinking that goes on underneath why those are there. Well, can you use just more transmit power on the AP? Does that fix the problem?
Typically not. So again, when we're looking at the overall ERP equation and just practically in real life, if you're just cranking up the volume on the amp, it's just going to broadcast louder and further. Yes, so the client device may be able to hear at that extra 50% distance, but it's not going to be able to talk back. You're not going to get both sides of the communication link. So it really doesn't really improve the overall coverage that you're experiencing in your environment. It's just causing more noise, more interference. And that's typically some of the problems that we see when we start to try to offset these in a standard environment, is that we're just making things worse rather than better by increasing the transmit power.
Well, I'll freely admit I made some major boo boos in my career. Many years ago, at least I haven't done this one for a long time, I found a manufacturer that made a 30 dB transmit amplifier. It it was supposedly also 30 dB upstream, but it was really only about 10. So it had about a 20 dB differential. And I thought, these are wonderful. We'll just stick them in and I get green everywhere. You know, somebody else needed 20 APs. I could get away with 5 because I just had these amplifiers. And then it took a while of troubleshooting my own mistakes to find it's not about transmit power. It's actually, you have to have communications going both ways. Well, you'd mentioned in the beginning that one way to correct it is to have better antennas, higher gain. So, higher gain on the client or higher gain on the AP?
So it can actually work both ways, just depending on what your client device is. Typically, that is going to be non-changeable. It's going to be a client device that has the antennas inside. Sometimes you'll get the use case where it's a printer on a forklift, and on those you can use a U.FL connector, and you can change the antenna. In that case, it does help changing the antennas to a higher gain model then. But for the standard deployment that people are going to be doing, it's really only the AP side that you can change. And even just changing the AP side and leaving the client all by itself, um, it can make a significant improvement on that mismatch. Um, and we'll kind of look at that in the practical portion of just how much of a difference that makes, even when you're looking at the same overall ERP value and changing the antenna gain to be higher and the transmit bias to be lower, but the same value, the performance difference is pretty substantial.
Well, that's in the, and we'll get to your practical results in a second. Can you just do a simple explanation when people say, if just to, and you said this, and I believe it, but I'm asking you just to repeat it from your experience. If I increase my transmit power, I yell louder.
Mhm.
If I increase my antenna gain, I still yell louder, but I listen louder, if that's a thing.
Yeah, so the classic example of this that people use to really demonstrate it is the megaphone example. So if you imagine somebody who has a megaphone, if they're screaming out into it, yes, they're screaming louder, farther. But then if they take that same megaphone and put it to their ear, Well, now they're hearing better at those farther distances as well. So you can imagine having a higher gain antenna because it's both transmit and receive, being a megaphone on the mouth and the ear to be able to receive and transmit at a higher level.
Great. Thanks for that. Well, let's get into how you. I'm guessing you just didn't do this data collection because you wanted to. Hopefully, you did it because you wanted a great WLPC presentation, so you collected data.
A little bit of both. I was also just kind of interested in the practical portion of it. So I was doing a little bit for myself, and then that kind of spawned this talk initially. But
Okay,
yeah, so
well,
just
tell us the problem and then your experiment.
yeah. So obviously the problem that we wanted to kind of test here is how much of a difference just swapping the antenna gain but keeping the overall ERP value make? How much of an improvement, or does it even make an improvement? Um, so to test this, I just did an AP on a stick test out in the middle of an open field. There was a park next to our office, using a WLAN Pi, which is a fantastic tool for AP on a stick tests, and then using similar but different AP models between the internal and the external. But the main thing we'll focus on is that they were 4x4s, and from the same manufacturer. The 4x4 will matter because one thing that we haven't taken into account yet on our ERP calculation actually is the MIMO gain. You do have to consider that when you're doing your overall calculation. So for a 4x4 four spatial stream AP, that's an additional 6 dB that we actually have to account for. Um, so when we're looking at these tests, everything kind of ends up being 17 dBm between the transit power and the gain of the antennas that we're calculating, and then the additional 6 dBm from that MIMO gain. So that's kind of the constants that we're dealing with here. And then set up across the board at about 175 feet, 50 meters from the AP on a stick test, just to keep everything nice and consistent. That is one of those things that we were talking about, Keith, that I may update also in the hopefully future presentation of this, is one, using 6 gigahertz potentially with standard power to really show the improvements on those client devices. And then two, changing the distances to one, show the consistent 50 meters, but then also what is the max range then with those higher gain antennas.
You'll end up walking more than 50 meters for sure.
Oh yeah.
Okay, so the setup is you have an AP one place that's transmitting with a what are the different types of antennas you're going to be testing?
Yeah, so the client devices, again, were the same across the board. They were actually connected, so we didn't use a Sidekick or a Nomad because those don't actually connect to the network. They just passively listen, but use an iPhone, an iPad, a tablet, which was an MSI Raider, and then a Pixel. So we kind of had a diversity on the client side, and then tested a range of different antennas, both from an internal model from the MIST AP33, and then using the MIST AP63, and a few different models ranging from a low gain 4 dBi, medium gain 7 dBi, and then a high gain 12 dBi antenna to really see the differences as you stepped up here.
So you changed that your baseline was a internal Omni,
Correct.
and then you switched to the same brand but one with an external Omni.
An external wide
I'm
patch.
sorry,
It's
an external
wide.
antenna, and then you changed out antennas. Okay.
Correct.
So when you did the baseline, you collected data. What was the data you were after?
Yeah, so the data that we were after is one, we had to pull down what the AP was actually seeing from the client, which that's not always the easiest thing. That's not something that's typically readily available in most dashboards or um, in most packet captures. Now, if you have 802.11k enabled, or if you're using some of the vendor provided programs, like Mist has their Marvis platform that you can actually see the client side as well, or sorry, the client to AP side as well. But I just did a dump from the AP side that would show me the client to AP RSSI values, and then the AP to client RSSI values at that exact same time. So it was
And you
actually
got
great
those
to
off.
actually see.
You got those off the client.
Oh no, those were from the AP. So I actually worked with one of my Mist SEs, and he was able to pull the dump logs from the back end, and it would show me the RSSI values across all 4 spatial streams, and then averaged, and then the what you would typically see, the AP decline RSSI value.
Okay. So what were your results with the baseline, just an internal Omni?
Yeah, so that 50 meters that we chose was kind of because of this. This was really the limit that you would see when using these devices. So For an iPhone, you typically saw a neg 66 AP to client, what we typically see, but on the client to AP side, you were seeing neg 74, so about an 8 dBm delta between those two, and then about a 6 megabit and 7 megabit down and uplink respectively. And that kind of was consistent across all the other devices. The iPad was about an 8 dBm difference, and then again the 5 and a 3 uplink. The laptop was obviously slightly better just because it has a slightly stronger antenna inside of it, so it was not as much of an offset. It was about 4 dBm with roughly the same up and down link at that distance, and then the Android was slightly worse on this test specifically at about 10 dBm difference, neg 64 to neg 74, but actually slightly better performance at 6.24 and 7.8 megabit per second on the down and uplink.
And I know for you people listening, this is a whole bunch of numbers just running by. We'll have the slides with the data supporting this. So Connor, we don't need the details. Let's just talk about what the differences are then. So you switched
So
up from
the main
that
thing that we're concerned
baseline.
about here is, yeah, that delta. So that roughly 8 dBm across the board average difference between AP to client and client to AP receive values.
Then you move to a low gain antenna, a 4 dB antenna.
Yeah, so this is approximately the same gain actually as that internal Omni in the AP, but this is obviously more directional antenna. But even with that, the improvement with just having the directionality also was a pretty major factor. So right off the bat, the difference became 3 dBm on the iPhone, 4 dBm on the iPad, 3 dBm on the laptop, and 3 dBm on the Android, and pretty significant improvements on actual performance as well.
So
Um,
about a 4 to 5 dB improvement with the same dBi antenna. It's just directional now.
Correct, yeah.
Okay.
And even on this one, the overall AP to client was roughly the same at neg 66, neg 67. But that difference on this, the hearing side of it, client to AP, was that improvement. There wasn't any change in the standard AP to client RSSI values.
Okay. You moved up to a little higher gain, a medium gain antenna. How did that change the results across the board?
Yeah, so again, we kind of saw that it was an improvement overall. So 3 dBm difference on the iPhone, but with a lower entire total. So NIC 64 and NIC 67. And that was kind of the same across the board. 6 dBm on the iPad, 3 dBm on the laptop, 1 dBm on the Android, but all those being pretty significantly lower on the initial RSSI value. So while the delta may be the same or a little better, the actual total thresholds also improved with that. The up and down links stay the same. And one of the things that I'll adjust on any future testing for this is setting up an iPerf server on the WLAN Pi. We were kind of limited on the cellular backhaul I was using for this because I was going in and changing all the transmit powers to keep that ERP the same. And that kind of limited me doing that. But in the future, I'll set that up to really max out the up and down link. But already seeing more improvements as well on the initial just delta between AP to client and client to AP RSSIs.
So the delta between the client mismatch as you improve the antenna didn't improve that much, but the actual downlink improved because you're more
Correct.
focused.
And that's part of the point when we get to that same distance is we're probably seeing some of that being at that 50 meters is we're seeing diminishing returns. You can't really get to a point where the client to AP RSSI value is going to be better than the AP to client most likely. So that's one limiting factor that's at doing it at the same distance. So that we are limited because of that, seeing a drastic improvement, but you can definitely see an improvement on the performance and the signal strength versus the signal strength.
So next up, it's probably your last one, is you went to a high gain, a 12 dB antenna, and what were the changes as you went to it? Well, I'm sure it had a narrower field because your directionality went tighter. But what did the clients, did they like that tighter gain better?
Yeah, so like you said, this was more of a 20 by 20. We typically use this for point to point or stadium applications, 12 dBi. So really maxing out, at least on the MIST client, you can only go down to 5 dBm transmit power. So this was the highest gain antenna you could possibly use with it. So with that, we saw a slight improvement on the delta between the RSSI on the iPhone. So 52, neg 52 versus neg 54. Kind of the same playing with the iPads and the laptops. So it's kind of maintained the same diminishing returns that we were talking about. But then the Android device actually got down to where it was only a 1 dBm difference. It was neg 52 versus neg 53, which was obviously very tight having that high gain antenna on there. It was hearing the client device very well at that 50 meters. So it definitely is preferring it at that end. We're not maxing it out as much as we can with that limit on the cellular backhaul, but you can already see just at this single distance with a single test that it was preferring this higher gain antenna versus the lower gain models or the Omni.
Okay, so you went out in the park, you set up a standard internal Omni, a low gain, medium gain, high gain antennas. You tested across 4 different clients. What's the key takeaway?
I would say the key takeaway is that it really does help having these higher gain antennas if you're planning to really max out the distance that your client's going to be away from the AP. If you're doing like a standard office space or school room and you're going to have a good amount of secondary coverage and easy roaming, it's not as much of a concern probably, but if you're doing outdoor spaces or warehousing where a lot of times you're planning your design to where the coverage from a single AP is planned to be all the way to the fringe edge of that cell of coverage to that neg 67. Having the higher gain antenna is almost required really to get the most benefit in those environments. Otherwise, you're not designing your network to actually plan for the client. It's going to be very poor performance on their end. So it's extremely important to consider using these higher gain external antennas in those more edge case where you're focusing on the edge of the cells.
Well, I'd like to back up and see if I can get you didn't cover this in your presentation, but I just want you to think about it. Internal Omni, about 4 dB. Mm-hmm. External 4 dB antenna. Why do you think there was a nice 4 dB, 5 dB differential on the client AP mismatch by changing out the antenna? They're both 4 dB. And so for people who are just hearing the 2 words, it's like, well, they're the same.
Yeah, so that could depend on the actual antennas inside the AP more likely. They may not be individually omnis. They may be a composite omni over all of them. So while 2 of the spatial streams may be heard very well on the AP, the other 2 on the opposite side may not be heard as well. So the overall averaged RSSI is that higher neg 67 versus when using a directional where all the antennas are focused into that single plane. It is heard across all 4 spatial streams to the actual client device, and that could be a better average then on the RSSI values.
So your low gain patch had what kind of directionality to it?
It was pretty minimal, so it's a 90 by 90 roughly. So
compared to a 360
compared
on the
to an
Omni.
Omni, yes.
Yeah, so I think that might be where we picked that up is because you're focusing both. It might have been the same amount of energy, but it was all focused in one place.
Correct, yeah.
Yeah. Well, Connor, thanks for taking the time and sharing this. We'll put the link to his presentation in the show notes. You can go and watch the presentation itself. I was going to say live, but you'll watch it recorded. If someone wanted to track you down, Connor, where would they find you?
Yeah, so I'm very active on LinkedIn. There's Connor Burke. I'm from Hubble Excel Techs. And then on Twitter or X, I'm at Wi-Fi Aggie.
Let me guess. Texas?
Yes, sir.
There you go. And how's your team doing this year?
Could be better. We still have a chance for the playoffs, but we got to win out, which we had to do anyway because we wanted to beat UT. So it was going to be the game plan either way.
Well, thanks for your time. You've been listening to another episode of Heavy Wireless, part of the Packet Pushers Podcast Network. If you have any questions or ideas you'd like to see, you can contact me, Keith Parsons. I'm on LinkedIn and also on Wireless LAN Professionals website. Thank you.